Hello, everyone. Just let me just let me make sure that live has been started. Now, Gravitation Unplugged started 4 minutes ago. Now, just wait for 2 more minutes. You can skip if you're watching recording. Let's start anyways. If now, today what we will do is we will start gravitation, and we will continue to let me make a gravitation sheet first. So we will be doing this in a revision mode, so it will be fast, but it will contain everything. It will have everything you need to know about gravitation. So let us start with gravitation. I guess I have taken into account this. Yes, I am here. Now let us start with gravitation. Now, now for gravitation, let us start from very beginning, from Newton. Newton observed something and said that the gravitational any two body having mass A and B, let them have mass m1 and m2. There exists a mutual force between them, and the force is given by F is equal to G times m1 m2 by r squared, where this is distance r, and this is m1 and m2. This is whole distance between them r, and this is universal gravitational constant, and this constant has value that is equal to 6.67 into 10 to the power minus 22 or 23. uh, Let me just now, yeah, 10 to the power minus 22. Now let us let us discuss about them in detail. So now, what is the limitation of Newton's laws of gravitation? Limitation is that it cannot be applied on extended bodies. Cannot be applied on extended bodies. Only if m1 and m2 are point masses, m1 and m2. Only if these two are point masses, then only they will follow the law F is equal to G m1 m2 by r square. Now there are we have devised several different methods. All extended bodies are also made up of very small point masses. So we will take that into the integration to find out the forces and everything. So yeah, there are different ways, but only for extended bodies it can be applied, and for spherical bodies. For spherical bodies, we assume spherical bodies to be point masses. Body. Now, since this have been done, let us just uh, let us just continue with this. Let us take a rod into account, and we have to find out the gravitational force on this rod. Any other mass m1 is there, and let's say the mass of this rod is m2. and the length of this rod is L. Distance between M1 and rod is R. Now, to find out the forces, we know that all the forces will be applied in this direction. So, if we will add the forces, we have to just do the scalar addition, and it will automatically give you the correct value. Uh, my video is live, right? Yeah, my video is live. So just let me check if my voice is clear. Yeah. Now R1. Now for M1, how can we write the force? And let us take any element of small mass dm at a distance x from M1. Then the force due to gravitation on mass M1 will be, on both of them will be F M1 dm by x squared by integration. Now we know that uh, GDM, sorry, G is always constant, M1 is always constant, DM is changing with x. So we will have to write DM as a function of x. DM we can say that is equal to mass per unit length into dx. So we can make this substitution. So this is M2, I guess. Yes, sir, this is M2. Now this can be further written as GM2, and DM can be written as M1 dx by L into x squared. Now every constant we have to take it out. Every constant we have taken here. Let me just decrease this. Yeah, perfect. Now after this, GM2 M1 by L into 1 by x square dot dx is the integration, and how we will put limits, it will be from R to L plus R. Now it will come out to be G M2 M1 multiplied by 1 by L plus R minus 1 by R. Yes. Now this will come out to be G M2 M1 by L into R multiplied by L plus R, and here it will be negative L. So let me just make this correction. So L and L will cancel out. This will give us the formula Gm2 M1 by R into L plus R. And is this one correct? Yes, this is correct. Yeah. Now, now. Let us just continue. Now let's just continue with further applications. Principle of superposition of forces. When there are more than two masses in a system, the force on any mass can be obtained by the vector. Like this was simple if M1 and M2 were there only, M1 and M2. But if let's say there is some other mass M3 also in the system, then there will be a force on M1 due to M3, force on M2 due to this, and on M3 also there will be a force like this. Now the net force can be given by the vector sum of these two, and that is why the force will come out to be like this and this on all of them. So let us just let us just solve a question. Let us just solve a question. Two particles of equal masses go around a circle of radius are under action of their mutual gravitational forces. Find the speed of each particle. So if two particles are going around a circle of radius r, so let's say this is particle 1 and this is particle 2, and this is their trajectory, circular trajectory. Now they are moving in a trajectory like this where the radius is small r. This is m and this is also m because they have same mass. They go around a circle of radius and under the action of their mutual gravitational forces. Okay. Find the speed of each particle. So now, since the force can do two things, either increase the separation or change direction. Since both of these are moving in a circle, and by symmetry we can say that they both will have same velocities, or yeah, they will have same velocities. Therefore, we can say that they will have same velocities. Therefore, we can say that here the gravitational force is only doing the work of changing their direction and not increasing the separation. So the net gravitational force is equal to the net centripetal force. So if they are moving with some velocity v, let's say with some velocity v, here is with some velocity v, then we can say that mv squared upon r will come out to be equal to g m m by 2r whole square. Now m to m cancel out, r will go there. Gm upon 4r, and that is the value of v squared. So v will come out to be under root of gm by 4r. Now, now let us just jump on some other derivations also. Derivation is not important, still I will do derive. The gravitational attraction of mass m due to the quarter ring of same mass m and radius r as shown in the given figure. Okay, so they have asked us the gravitational field due to the quarter ring. Now there is a mass of m and the total mass of this ring is also m. We have to find out what is force on m F due to gravitational interaction. Now here, now we know that this is not a point mass, so we will have to divide it into various smaller point masses of mass dm. So now comes the important part: how to divide them. Now let us take along their angular bisector some uh, at an angle theta. If there is an element of d theta, now at an angle theta from the center, from this point, if we take element of d theta, then uh, if mass m is divided in equal angles in pi by 2 radians, then theta will have, then theta radians, then angle subtending, then the part of the r subtending angle d theta will have this as the mass. So we have found out the dm by unitary method. If pi by 2, if the arc which subtend angle pi by 2 has mass m, then arc which subtend 1 radian has mass m divided by pi by 2. and we have multiplied it by d theta for the d theta. Now, after this has been done, let me make another clearer picture for you. I guess I should use shapes here because to make some neat figure. Shape. Now this is the shape, and one. Now, yeah. Now just erasing this part. This is irrelevant. Now we know that every mass dm will be, and if this is theta, will be having a force like this on this F, and this F can be again divided into two smaller components, uh, which will be F sine theta, and one will be F cos theta. Now for every mass dm at an equal angle along the angle bisector, another mass dm is also present. So all the F sine theta components will cancel out. And since all the F sine theta components will cancel out, therefore, therefore, what we can say is, uh, what we can say is, F sine theta component would be like this, or no, sorry, my mistake. F sine theta component won't be like this. This is not F sine theta component. F sine theta component will be like this, 90 degree to F cos theta component. Now, all the F sine thetas will cancel out on this part also, and the net whatever will be there in the vector sum will be F cos theta. So we can use, instead of vector integration, only scalar integration, and then do the integration of, now force is equal to integration of gdm m by r square, r is constant, into cos theta. Now gm upon r square into integration of 2m by pi d theta dot theta. Now this integration d theta dot cos theta. Now cos theta will be, cos theta will have, now will become sin theta, and we will apply limits from minus pi by 4 to plus pi by 4, and this will give us root 2 plus root 2, finally 1 by root 2 plus 1 by root 2, finally root 2. So 2 root 2 gm square by r square into pi, 2 root 2 gm square by r square into pi. Yes, that is how we do it. And now let us go to a new concept called gravitational field. So we all are we are all are we all are well aware of the concept of magnetic field, how magnets behave. Gravitational field. So there is a similar kind of idea. Since gravitational force is a conservative force, it also creates a conservative force field around itself. Conservative conservative force field around itself. And that conservative force field, and in that conservative force field, if some mass m is present there, it will experience some force. Now, how do we calculate the gravitational field strength? We just assume this small mass to be 1 kg. If there is some gravitational field, then whatever force will be applied on mass m due to that field, on 1 kg due to that field, will be its gravitational field strength. So for testing gravitational field, we just put a test mass m naught and finally divide it by m naught itself to get 1. So yeah, basically the force experienced per unit mass in a gravitational field, in a gravitational field, is called gravitational field strength. Now, since gravitational field strength, now now gravitational potentials, gravitational field strength due to point mass. Yes. Now, since force is equal to g m naught by r square, if we have to do m naught is equal to 1, we get field strength, or g, that is g m naught, g m by r square. In If there is only one mass in the field, if the field is due to only one mass, then this g is equal to acceleration due to gravitational force, numerically equal to. Now, due to extended bodies, again we can use integration. For example, as we did in rod, the formula came out to be gm by r square, gmm not by r square, into 1 upon r minus 1 upon r plus l. So this won't be r squared to make dimensions gm not by r. Oh, sorry, l was here. Sorry. Now, if here we put this m naught equal to 1, we get the formula of field E m by L into 1 by R minus 1 by R plus L. Now, this is the formula of field. Again, for an equatorial point of rod, we can just, for the sake of uh, revision video, we can just do what? We can remember the formula. Well, its integration is actually very interesting because we have to make a substitution of x is equal to I tan theta. But still, just for now, just remember gravitational field due to this on point P, on an equatorial point P, is 2 gm by r under root of L square plus 4 r square. Now, learning it in this form would be difficult. That is why another form you can remember it. Gp is equal to gm upon r into under root of L by 2 ka whole square plus r square. Now, what you have to remember is it is mass. This is the distance r. This is distance L by 2. So basically, you have to firstly multiply this distance and then this distance to get the denominator, and the numerator will be same. You can remember like this. Okay. So let us take example of a ring. For a ring, on its center, for a ring on its center, on its center, the net gravitational potential strength will be, gravitational field strength will be zero. Why it will be zero? Because all the masses are, or for all masses dm, applying force F on this, there is another opposite mass dm at the same distance that will again apply a force F on this, that will make the net vector zero. If there is a small gap in between the ring, like if this part is not present, then the net gravitational force will be equal to the gravitational force applied by the opposite part, there is no because there is no other dm against it to cancel out the vector sum, so it will be always equal to the force applied by the small part that has been cut out but in the opposite direction. Now this was ring on the center. If there is on a axial point of a ring, you can remember the formula of it as it is equal to gm into z upon r square plus z square का whole power 3 by 2. gmz. Mm, is this formula correct? The dimension of the lower should be 1, should be r squared. Now, z has length 1 and this has length 2 ka power 3 by 2 L3. Yes. So it will give out L2. Yes, this formula is absolutely correct. Now, how can we remember this? R square plus z square की power 3 by 2 upon into gm into z upon r square plus z square की power 3 by 2. We will have to remember this. As such, I cannot see any such trick to remember this. Due to some circular arc subtending uh, angle theta, we can do the integration in all the specific cases. And then comes the gravitational field due to a sphere. Now, gravitational field due to a sphere. How much time have we have left right now? In 1 hour, uh, we have quite time. So yeah, if there is a sphere like this, and at its center, we have to find out the gravitational field strength. Then it will be obviously zero. Hollow sphere we are talking about. And at any other point also inside the sphere, the net gravitational field strength will be zero, because the ratio of this angle, this solid angle, and the area subtended by it becomes equal, and that is why net force, net vector sum of all the forces becomes zero. And you can just remember it, since this is a hollow sphere, the gravitational field strength of any point inside it will be zero. At the surface point, the gravitational field strength will be equal to gm gm over r square, and at a distance x from its surface, it will be equal to gm over r plus x ka whole square. So if we will plot the graph for it, if we will plot the graph for it, it will be 0 till this point, till we are inside the sphere, and then after that, from this point onwards, it will decline. I guess this will be the graph. 1 upon x square the graph, yes. G is inversely proportional to 1 upon x square. This is x, this is g. Till here, and this point will be r, and here it will be gm over r square. Now, this was all about, it was all about sphere, hollow sphere. Now let us talk about solid sphere. Let me take the shape. क्या हो रहा है यार? Now, if this is a sphere and this is its center, obviously on center, uh, the gravitational force, the net gravitational force will be zero. But at a certain point P, let us take a point P, P outside, P inside, and P inside, and P on surface. Now, for P outside and P surface and P outside, we can concentrate this whole sphere into a point mass here. So that will give the formula F is equal to Gm over R square for surface, and F is equal to Gm over R plus X ka whole square for any point outside. But for inside, we can, for any point P, which is here, let's say at a distance x from it. Now we know that all of these, all of this area, all of this volume is nothing but the accumulation of a lot of a lot of smaller hemispherical shell over it, and hence the net gravitational field strength due to all of those will be zero on that surface. Now, for any point here, again we can concentrate this sphere into a smaller sphere, and then write the formula of gravitational potential strength as equal to Gm over x squared. So yeah, this was the first part of the video. For the next part, I will be explaining all of these strengths and potentials and everything. Thank you for watching.